Hi guys, and welcome to the latest in the Motion and Forces series for Year 10 Science. This video is video number 4, looking at Newton's first law. So we haven't really talked very much about forces so far. We've talked about how we describe motion in terms of initial and final velocity, in terms of time, distance or displacement, and also acceleration. Now we need to have a look at what's actually causing acceleration. And acceleration is caused by the application of a force. A force is needed in order for objects to accelerate. We're going to use the symbol F to represent force, and its unit is the Newton, after Isaac Newton. This is represented with a capital N. So we could, for example, write force is equal to 10 newtons. Force is a push or pull or a twist acting upon an object as a result of its interaction with another object. There are a number of different types of forces that you may be aware of, things like a gravitational force, an electrical force or electrostatic force, and also magnetism is also a type of force. So there's a number of different types of forces that can cause objects to accelerate. And we're going to look at specifically how some different types of forces can be used to analyze different situations of objects in motion in order to see if we can understand a little bit more about what's actually going on. So in order to do this, we need to look at Newton's laws, and Isaac Newton is really one of the founders of modern physics. And even though many of his equations have been subsequently replaced or improved on by Albert Einstein, his laws of motion describe most of what we experience on Earth in a fairly reasonable and predictable manner. And so we can use his equations and his laws to help us analyze most of the sorts of motions that we're going to encounter, particularly in our sporting examples. What Newton did was he gave us 3 very important laws, and these 3 laws explain most of what we understand about the nature of motion. Most of what Newton found out came in a book that he wrote, a scientific treatise called the Principia, and it outlined most of the key things that he understood about forces and motion. In particular, he outlined the 3 laws of motion that we'll look at over the next 3 videos, and also his law of universal gravitation, which was something that was, again, very important, but not something that we will spend very much time looking at in this particular topic. So Newton's first law then. So we'll split these next 3 videos up into a focus on each of Newton's laws. So the first of these is obviously Newton's first law. Newton's first law states this: an object remains at rest or in constant motion in a straight line unless acted upon by a net unbalanced force. That's a big mouthful, and effectively what it means is force is a vector. So therefore, a force has both magnitude and direction. And so as a consequence of that, force is going to be applied to any object in a specific direction. If there is no force being applied, then that object will continue to remain in whatever motion it is currently in. So if its velocity is 0, then it is at rest, and therefore it will remain at rest. If its velocity is 10 meters per second, then it will continue on at 10 meters per second in the same direction indefinitely, unless it's acted upon by a net unbalanced force. So unless something pushes it from one direction or pulls it. Newton's first law is also known as the law of inertia, and inertia is a term that we use in science to describe something that resists a change. So particularly a change in its motion. So objects tend to remain doing what they're doing, which could include doing nothing, as long as they possibly can. So you need forces to be applied to them in order to change that motion. If two forces are equal in magnitude and opposite in direction, and they both act on the same object, then we say that the object has a zero net force or zero resultant force acting on it. So therefore, if we have an object that's at rest and there is a force in this direction, and let's say it's 10 newtons, and there's a force in this direction, which is an equal and opposite force, and this force is also equal to 10 newtons, then we have the force net is 0 newtons. There's actually no overall force acting on this object. So there may be more than one force being applied to an object, but if the overall force, if the sum of the forces, or if the resultant force is equal to 0, then the motion of the object will not change. And if those forces sum to 0, then that means that the acceleration must also be 0. As we mentioned in the previous slide, another way to look at Newton's first law is to think about it as the law of inertia, or the law of resisting change. Sometimes when we're moving, it's hard to actually tell whether we're moving or not, or at least how fast we're moving, and that's a very relative term. You may have been traveling on a freeway at some point where you've been traveling at, I don't know, 100, 110 kilometers per hour, and then you slow down as you enter a city or a more built-up area to maybe 60, and it feels like you're really crawling. You're going really, really slowly. A lot of our motion is relative motion, and sometimes we need to sort of understand that motion in terms of a change. And when a change comes, particularly if that change is a very sudden change, then it can cause quite a sharp change in our own motion. So if we turn a corner very sharply, or if the brakes are suddenly hit on the car that we're traveling in, we'll be thrown forward. That sense of being thrown forward, or an unexpected movement, is what inertia is. Inertia is that resistance to change. It's why we wear seatbelts, it's why we have airbags, because the objects in the car that are traveling at 60 will want to continue traveling at 60 kilometers an hour, even if the car is being suddenly braked. So the car may be stopping, but the occupants inside it will continue to keep moving unless something else acts on them, or at least tries to slow them down. Now, the other thing about inertia is inertia doesn't just act on moving objects, inertia acts on stationary objects. Okay, if you're trying to get a very big rock to move, it's harder to actually get it moving than to keep it moving. Once it's moving, it tends to want to keep moving. You can sort of apply less force to sort of keep it rolling than what you have to apply initially to get it starting to move. So the net effect of inertia is to keep an object in the same type of motion. So it tries to preserve that motion, whether it's stationary or whether it's moving. It tries to keep doing what it was doing before. And inertia is directly related to mass. So the larger the mass, the more the inertia of the object. It's harder to get a very large object moving, or to stop it from moving, than it is a smaller object. I've sort of already alluded to this, but inertia is a critically important thing in cars, and a lot of the technology that we have nowadays is going into ways of trying to minimize damage that can occur, particularly to people in a car accident. One of the significant breakthroughs was just the wearing of seatbelts. It saved a very large number of lives, just the mere fact that people had something which just slowed their motion down a little bit when the car was being braked. It wasn't throwing them into windscreens or into the dashboard or into the seat in front. And this is because our bodies continue to move because of inertia. If we're traveling at a certain speed, and the same thing is true if we're stationary. If you've been in a bus that takes off suddenly and you are stationary and you're just standing on the bus, if you don't hold on, that sudden forward movement of the bus can actually throw you backwards. It's that sense of feeling like you're moving backwards. But all you're wanting to do is remain in the same relative place on the earth, but the object that you're in is wanting to move past that point. And so therefore, it makes it feel like you're being thrown backwards. And the same is true, obviously, if you're moving forward. So Inertia acts both, as we said before, on moving objects and on stationary objects. So questions around Newton's first law are very much about what happens to moving objects or stationary objects when there is a zero net force acting on them. So the key to this is if an object is moving in a certain direction and it has a certain speed, let's say its velocity is equal to 5 meters per second, then irrespective of whether there is zero forces, two forces, or 200 forces, if they all balance each other and the net force is 0 newtons, therefore there is no acceleration. And if there is no acceleration, then the object must remain in its present state. So it will continue to remain at 5 meters per second in this kind of sort of easterly direction, if we call this east, moving in an easterly direction. Newton's first law says an object will remain at rest or it will continue to move at a constant velocity unless it's acted upon by a net force. So Newton's first law, Newton's first is about the application of zero forces. Thanks for watching.